When two current carrying conducting plate is separated by an insulator or a dielectric, a capacitor is formed. So these two plates, these are current carrying ones, and the inside here, let's call it like that, this is an insulator, or it is called a dielectric, and this structure is a capacitor. And when this kind of structure is connected to a voltage source, let's say a DC voltage source of voltage V, what will happen, this positive charge here will get deposited here. So it will have a positive charge on the plate and it will have a negative charge on the plate. Here on this plate there will be the negative charge, and on the upper plate it will be the positive charge. And in the end, this will take some time, but in the end the voltage across this one will be V. So the property capacitance, which is the measure of capacitor, is given by this equation, which is Q over V. This means that the property of a capacitor, the value of a capacitor will be high if it can store more charge with the same at the same applied voltage. So the ability of its storing charge is a measure of capacitance, it can be said. Though it doesn't depend on either the amount of charge or the voltage, it actually depends on this equation, which is epsilon. This is the dielectric constant of the insulator here, or the dielectric material here, and times A over D. So A is the cross section of this plate. So if the plate is like this is the cross section. So this will be somewhere here, I'm not drawing it, the lower one, but the upper one is like that. So the cross section will be A, and D is the separation here. So that's D. The more the separation, the less the capacitance. It makes sense. So that's the value of capacitor. And the current here is given. We know that current is dq over dt, and if we substitute q, we can see here, we can write q is equal to vc, so that will be c dv over dt. So instead of q we can write cv. So that gives the current through the capacitor, and the current is like that. The current through a capacitor is expressed like that. So when a voltage is DC, there is no change of voltage, there won't be any current. But in case of AC, there will be a current through the capacitor. So when the applied voltage is DC, there won't be any current. There will be a slight current, a transient current, while the charge are getting deposited on the plates, but after that there won't be any steady state current for the case of DC. But for AC there will be a current, and that is given by this. And also this expression tells us that the voltage across the capacitor cannot change abruptly. It has to be a continuous change. So the voltage across a capacitor cannot have this kind of slope. It cannot be the voltage. It is not possible. This can be the voltage where the change is continuous, or it can be like that. This is a continuous change. This is fine for the voltage across the capacitor. Because why? Because if the voltage changes abruptly, that means this one is infinity, because the angle here is 90 degree and tan 90 degree. This is the gradient of the voltage basically. dV over dt is if the voltage versus time, if we plot, this one is the gradient, and if the voltage changes abruptly like this one, the gradient is 90 degree, the angle is 90 degrees, so the gradient tan 90 degrees is infinite, so the current will be infinite. Or practically, if we want to have an abrupt change across the abrupt change of the voltage across a capacitor, the current we will need is an infinite current. So it's not possible practically. So this is one thing of the capacitor, that the voltage cannot change instantly. It has to be continuous change. So that's that thing. And if we talk about power, so capacitor is not a energy dissipating element like resistor. It is an energy storage device. And if we talk about the energy, power is like VI, or tau, let's say d tau here. So we can say this one is V, and this will be C dV over d tau and d tau, and this is then C dV and then V here, like that. So from 0 to, let's say this is minus infinity to t, minus infinity to c. Minus infinity is before it started, so before this one the voltage was 0 because nothing was connected, but when t was minus infinity the voltage is 0, but when t is equal to, when tau is equal to t, the voltage is V, if we say it. So if we do the differentiation, we get V dV, differentiation is V square over t, so basically V square over t, and then V square over 2, sorry, V square over 2, and this one is V over 0, so basically half CV square. So this one is the energy, sorry, not the power. The power P is equal to VI, so energy is the integration here. So that's how we get the energy from minus infinity to t. So this is power, and energy we get like this. So t and then PD tau, like that. So that's the energy. So this is the energy stored in a capacitor. And yeah, that's pretty much the introduction for a capacitor, I would say.